Hey, we study cross product and Heron's formula. When I was a high school student, I learned in high school the Heron's formula for the area of a triangle. But at that time, when I learned it, I didn't learn any vector. So the derivation was very tedious, and the result, it seems remarkable, but the mathematics teacher told me how to apply that formula, memorize the formula. But I don't like to memorize the formula. I do want to derive a very interesting formula based on what we learn. So you are now familiar with the vector, and this vector is very, very convenient because it is a very nice tool to deal with geometry. It is mostly developed by, not by mathematicians, but by physicists. And the extreme development was made by Heaviside. And even Maxwell did not use a very convenient contemporary way of writing vector. And Maxwell's equation, we learn nowadays, is the representation of a vector constructed by Heaviside and Gibbs. We are now considering a triangle. And when we learn triangle or parallelogram, cross product is a very nice tool to deal with the area, to compute the area. First, let us introduce a triangle. I'd like to introduce this one of our K-pop paper. It is a very, very interesting paper. You can freely download this paper from the European Journal of Physics. So we have A vector, B vector, and C vector. If they are connected in this manner, head and tail, head and tail, head and tail, then you follow up to make a complete sum. Its final result is a zero. It is equivalent to, right, in this manner. So any triangle side has a corresponding side vector, and all three side vectors are linearly dependent. Because its triangle is constructed on a two-dimensional plane, we do have only two basis vectors that are linearly independent. So this demonstrates the fact that the three vectors are not linearly independent, and they are linearly dependent. So there are various ways to write down the area of a triangle. First of all, show that the area of a triangle is this. So you're now familiar with the vector notation. So high school students do not know how to compute this, but now you can. First, why don't you draw a carbon copy of this congruent triangle? Then you can construct a parallelogram. Area of a parallelogram is a product of base and height. And how can I compute this height? I can choose a base, but height is what? If I choose a C, there is an angle. C sine theta will be the height. Or if I choose this angle theta prime, then B sine theta prime will be the height. So base times height is the area of a parallelogram. And because these two areas are the same, the congruent triangles, therefore the area of a triangle is area of a parallelogram multiplied by 1/2. Okay, that's it. But what about how can I compute the sine? Sine is this is a positive number because the angle runs from as though, so sine theta should be computed in such a manner 1 minus cosine squared. because it is a sine is a positive, it's the same as the square root of sine squared, and because of the Pythagoras theorem, it is 1 minus cosine squared theta. And what should I do with the cosine theta? This cosine theta is the angle between the two vectors. Here, these vectors AB, BC, and CA. Okay, that can be computed using A dot B divided by magnitude of A and B. If I want to compute the square, the result is like that. Therefore, the area of a triangle is product of the two magnitude of two sides and angle, sine angle. BC, sine angle. CA, sine angle. And that sine angle square should be computed in terms of 1 minus cosine squared. So using this replacement, the sine is replaced with 1 minus cosine squared everywhere, and then substitute the result for cosine is the cosine between A and B is, what's that? A dot B divided by magnitude of A, magnitude of B. Substitute this one into here, I finally find it is this, right? Therefore, I can combine these square roots. Then I find it is a squared b squared minus a dot b squared, b squared c squared minus b dot c squared. So you should be able to find the structure. It is a product of the two sides multiplied by sine. And sine can always express in terms of 1 minus cosine squared, and cosine can always express in terms of the scalar product. Okay, that's it. Next, prove Heron's formula for the area of the triangle. Area of a triangle can be computed using the length, side length of a triangle. Remarkable. If I know the length, three lengths of a triangle, then I can compute the area exactly. Okay, what should I do? I know this is 0. Because of this, a plus b equals minus c, b plus c equals minus a, and c plus a is minus b. Why don't we square these formulas? Haha. And then I can expand this. What's that? I can express this in terms of cosine theta between the angle where theta is the angle between the two vectors. This is nothing but the second law of cosine. You remember in high school you learned the second law of cosine. Okay, using this second law of cosine, I can substitute these guys into the formulas. Why I need this? I know the area of a triangle is 1/2 of square root of a squared b squared minus a dot b squared, and so on. And why? Why don't we replace the angle-dependent term in terms of, by making use of the second law of cosine? So substituting second law of cosine, I find a very strange formula. A little bit complicated, but I can expand this in principle. Why don't you pull out the 1/2 inside of the square, then it becomes 1/4, and we combine these two pieces, so it becomes 4 times a squared b squared. You know how to expand this. A little bit busy, but first of all, square, square, square. So a to the fourth, b to the fourth, and c to the fourth. You know, a plus b plus c squared is equals a squared b squared c squared, and plus multinomial expansion 2ab, 2bc, and 2ca. Okay, so I have completed the expansion in this manner. We remember one is a positive, the other two is a negative, so be careful about the sign. After that, we find it is only this guy has a plus 2 and the other the minus 2. However, we have this guy, and if when they combine, there should be a mistake, right? There is something wrong. The answer should be in this manner. What's wrong? C to the fourth minus B to the fourth minus A to the fourth minus, that's fine. CA is a minus 2C squared A squared, but because of this, it should be plus. So there is a sign mistake. This is a minus, this is a plus, and this is a plus. Okay, so, and then I flip the sign, negative sign, pull out the negative sign. After that, it becomes all negative sign. Okay, so this expansion gives this. And we can factorize this in the next step. Anyway, this function is called Kellen function. This is called Kellen function. Kellen function, particle physicist. My major is a theoretical particle physicist. And this function appears in the special theory of relativity, a very interesting formula, but you will learn later. Okay, anyway, we have completed the fact area of a triangle of this kind of form. And this, what we have done is with the two sides A and B, but we could have done with the same job with the BC and CA. The final result is the same. As a result, we'd like to finally derive the Heron's formula. It is completely factorized in this manner. We have a very symmetric expression in here. Why don't we factorize this? You could have done with this because it is a squared subtracted by b squared style. So it is always factorized into a plus b and a minus b. So even though you don't know this previous step, you could factorize this. Let us return to high school and let us factorize this formula. Simplify in terms of a single variable. There are A, B, and C, so why don't we choose A? A to the fourth, A squared, and independent A. Aha! This is factorized into B squared minus C squared squared. Okay, we are almost there. This is A to the fourth, A to the square. Why don't we replace a squared equals a z? This is a quadratic expression. Something like x plus y z plus xy. Aha, middle school student can factorize this in this manner. And why don't we replace the z with a squared? So this is the answer. What we have to do is to find out these combinations x and y to satisfy the expansion formula. The answer is found in this manner. And finally, we keep on factorizing this and this. This is using the a squared minus b squared equals a plus b times a minus b repeatedly. Finally, we end up with this factorizer formula. It is quite impressive. This is the sum of the three sides, and this is the difference of sum of two subtracted by the other, sum of two subtracted by the other, sum of two subtracted by the other. Any middle school student know very well about the sum of two sides of a triangle is longer than this. So this is positive, and this is positive, and all of the side lengths are positive. So the whole thing is negative definite. If ABC constructs a triangle, this Kellen function must be negative definite. As a result, we have a sign difference over sign negative sign. So put the negative sign on it, then minus lambda is a positive definite. That is the area of a triangle. It is called Heron's formula.